And this is what those data look like. This is not a gridded data product, it's not interpolated lines, these are actual individual data points. So this is about 150,000 measurements of the CO2 content of the water from the surface to the bottom, from essentially the shore out to beyond the shelf break at Cape Perpetua. The color here represents the CO2 content of the water, and the location of the symbol represents its depth and longitude in the cross-shelf distance. What you'll notice here is that you see a lot of red down here in the deep water. And it's red down here at the source, and it's red up here on the shelf, and this is because the source water is flowing up onto the shelf during that flow. But there's a lot of really deep purple up here at the surface. Okay? And if you take those individual surface points and you look at the CO2 partial pressure, in comparison to what it would be if it were in equilibrium with the atmosphere. Now this is from 2001, you'll have to know the atmosphere today is about 390. But in 2001, this water was strongly undersaturated, depleted in carbon dioxide relative to the atmosphere. And so, if that's the case, that means that the Oregon coast has to be taking up carbon dioxide from the atmosphere. And it really surprised us for a while, but we finally think we understood why that was the case, and finally published the paper. And it looked like it wasn't just that one time. We did lots of sections across the shelf, from Cascade Head down to Cape Perpetua. That's all these different symbols here, and they're all really high. They're high very near the shore where you see the upwelled source water, but they're low across most of the shelf. And it's true over time as well. This is a series of cross-shelf transects at Cascade Head, where again you see the high concentrations very near the shore, but low concentrations seaward of that. And we also went back in August and saw the same thing. Very high concentrations down at depth, but very, very low concentrations in the surface. And it looks like when winter downwelling happens, all this extra carbon dioxide looks like it's been added between August and May. Winter downwelling just moves that water out, just sort of empties the trash. Okay? It moves this high carbon dioxide water into the ocean interior. These are nitrate profiles, also from the supersucker. This is from Cascade Head, so we can measure nitrate concentrations on the same sort of time and space scales. And while we were doing this, another group at Oregon State was doing high-resolution turbulence measurements with the freefall vehicle. So we were towing ours off the side. It was going up and down. And these guys were off the back, just throwing their instrument off the back until it hit the bottom and then reeling it back up. And it was a really amazing ship operation feat. We had no idea how hard it was to do that until the Scripps guys tried. So what we showed here is the nitrate concentration and the nitrate gradient calculated from the concentration. And this is a measure of the turbulent mixing. And what you see is that you have very high nitrate gradients here at the inshore where they match up with very high mixing rates. And that drives these very high nitrate fluxes. So what happens is the high nitrate water flows up into the inshore, high turbulence there, mixes it up into the euphonic layers and the illuminated layers, and that's what fuels the elevated productivity of the nearshore waters. It turns out that there's some extra nitrate in that water, and that's enough to take that carbon dioxide, that high carbon dioxide in the source waters, down from its high initial value, not only to atmospheric saturation, but to levels far below. Okay, so that's why it's a sin. Okay, second part here. It looks like most of the organic material produced during these summer blooms, now these are what are responsible for drawing down the nitrate, consuming the carbon dioxide in the water. It looks like all of that material, shown here as particulate organic carbon, is exported into the deep ocean. And the way we did this is we took some sections of oxygen concentrations, also collected with the supersucker. We measured wind speed, we measured the difference in saturation between oxygen in surface waters and in the atmosphere. We looked at the velocities in the longshore transport, we calculated the fluxes of oxygen and carbon. And I'm not going to worry you with the details of that paper, but what we found is that the oxygen data, you compared what we saw in May and what we saw in August, said that this system had to be producing a tremendous amount of new carbon, of new phytoplankton carbon. And if you looked at the POC data in detail, it actually looked like maybe there was less in August than there was in May, right? So the oxygen says it absolutely has to be being made. POC data says it's not there, right? So it's got to be going somewhere. And what we think is that during these relaxation events, all this material down here in the bottom boundary layer is getting pumped out to the shelf edge and dumped into the open ocean, okay? And so we really like the trash man analogy. When the trash man comes once a week, you sort of never notice. The trash man doesn't show up for a month, things get pretty nasty. And that's really what happened in some of these extreme hypoxic conditions here, is that we didn't have relaxation events that pumped this material out. And what we found is that if you look at the reactivity of this material, and so this is the carbon dioxide change in incubations from bloom material. We sampled some water, grew a bloom and really abundant nutrients, and then took the nutrients away and the bloom crashed. We took that material and we put it in the dark, and we watched how fast the carbon dioxide rose. And what you can see is that this material here, this is the whole water, and this is the filtered water. And the difference between the filtered water and the whole water is telling you how much reactivity or how reactive the particular organic carbon is. What I want to point out here is that these are hours, not days. And this material is highly reactive on the time scale of several days, a week or so. So if this material doesn't get exported somehow, it's going to degrade. And what happens when it degrades? Well, you consume the oxygen, right? Now this red line here is the hypoxia threshold. This is the 2 milligram per liter or the 1.4 milliliter per liter threshold. I despise those units, and so I'm using something the chemist would like. And it turns out this is about 70 millimole per cubic meter or micromole per liter. They're interchangeable. And what I wanted to point out is one of my favorite all-time quotes in the hypoxia story is it happened for the first time in 2002, and it's happened every year since. And this is from 2001, so I like to say this is from the year before it happened for the first time. And what you can see is that even in May, we have some hypoxic waters off Hecate Bank. But by August, we've got hypoxic waters that almost span the entire shelf and actually go far up into the water column, up within maybe 40 meters of the surface. So this happens. Now, there's some suggestion that maybe it's happening more in the last 10 years than it has previously, but it happens fairly frequently. And even though there's widespread and intense hypoxia, we didn't have a die-off. So you have to have really sort of extreme hypoxia before you have the real mortality events that really grab the press's attention. And I just had to do this because it's so much fun. But this was the paper that really got people going. It was this Nature paper in 2004 that was about the 2002 hypoxic event. And pretty much any time somebody measured an oxygen concentration between 1.4 milliliters per liter, the newspapers found out about this, and things just really started to get more and more out of hand, and these were sort of the more responsible ones, and then, you know, it was puzzlingness and killing the animals, and then we had to go out and combat it. And then this is my favorite one. This is from the Oregonian, you know, dead zone snuffs life off the coast, you know, tackling them. You know. So anyway, these are, you know, it's another one of these things, and the folks that actually are working on this more actively than I am just can't stand this dead zone terminology that the newspapers just eat up, you know. So anyway, just remember that we're sort of sensitive to these kinds of conditions, and one measurement of below 1.4 milliliter per liter oxygen doesn't necessarily mean that all the rockfish are dead on the coast. And you know, people are working hard trying to figure out why, you know, what the real tipping point is in that, if it's not this sort of traditional threshold.